Hey everyone, I hope everybody is doing great. Today I have come up with a surgery where I have received a model for an indentation test from a subscriber, and I will make this model work, and not only work but work correctly. What you will learn is you will learn step by step model troubleshooting, how to get a hysteresis, which you see on the right hand side here, and also if it's a load control test rather than a displacement control test, then how to change the loading and boundary condition. And finally, obviously, you need to get a nice pattern, as well as you need to get the hysteresis which you actually capture during your experiments. So if you want to learn all these things and also other tips on the way, then please proceed, and I look forward to you on the other side. Thank you. Hello everyone, welcome to this video. Today I'm going to quickly go through a model which has been sent to me by a subscriber, and this model is about nano-indentation. I already have a couple of videos on my channel on nano-indentation. So the user has asked a few questions. For example, it's being asked that how to apply load rather than the displacement as a boundary condition or loading in this model, because the actual test is being done as a load control test most probably. So they have a load displacement curve and they want to compare it directly from that. And also if there are anything else which I can suggest to make it work. So let's quickly look at the model and see how this has been constructed and whatever I can suggest to improve the model. Okay, so this is a kind of a specimen, I think, as it was in my 3D nano-indentation tutorial. And then there should be another part, and in this case they are using ABAQUS type indenter, which is very much the same which I used in my model. I can see a reference point, so most probably they kept this as elastic, but let's check that in the property module. So now if you go to the property module, we have elastic properties. So density is specified, and this is again in per millimeter cubes. So it seems that the model is in millimeters. And then the Young's modulus, which is in megapascals, steel, looks like steel, and Poisson's ratio. Then solid section, and there is only one solid section which uses the material one property as solid homogeneous. And then there must be an assigned space, and then this would have been assigned to this part, and it might have been done for the other part as well. So this seems, yeah, it seems like both parts are made up of steel at the start, and this means both parts are made up of elastic deformable objects. So we can check that here, and both are 3D deformable. Now we go to the next step. Again, there are two models files in this actual CAE file. One is, I think, standard, and one is explicit. So I'm just going through this explicit first, and I think most of the things which I will be mentioning or giving the tips on will be valid for both the cases, and I will try to be explicitly giving you other ideas for the standard as well. So this is the assembly, and again you instance the part and you bring it here as I have shown you in the tutorial. Again, if you look at the step definition, it's a dynamic explicit step with 1 second, and everything else seems to be default. I'm not sure why they're going for dynamic, but I will just take it. Maybe they required it to do it. Then interactions. So it seems there is a rigid body interaction here between the part and this, because this part is elastic. So let's look at the rigid body constraint, and you can see there's a rigid body constraint here. So this part is constrained with the reference point, and most probably the boundary conditions or loading will be applied to the reference point. Anything else here? There should be contact properties. So if you look at the interaction properties, so these are the contact property. General contact has been used. So explicit gives you this option that you don't need to define precise surfaces, but rather you use a general contact, and ABAQUS or during the solution automatically detects if there are any surfaces which come into contact with the other. And this includes the self contact as well. So if you have a part which has a very large deformation and different areas of the part are come into contact with each other, then you can use self contact as well, and that's also included in general contact. For interaction properties must be default. So tangential behavior is frictionless, and this is hard contact, and they allow separation as well. So this looks fine to me. If you go to the loading now, then there is no force, and this is the question that how to apply force. And then there are displacements. So this is bottom where everything is fixed. Then this is fixing in all other direction the reference point, and then this should be the vertical displacement in z direction, which is 2 in this case, which means it's moving in 2 millimeters. Since the components are very close to each other, so maybe it should be okay, but I'm not sure. And then there is an amplitude function, as you see here. So let's look and explore what this amplitude function is all about. So we go to tools, amplitude manager, and then edit, and then you see it's just going down, and that's it. So there is no other way around it. So if your loading was done with a precise sort of a data where you apply certain parameters in your test and you want to specify those, then you can basically try using that as well. So this looks fine to me. Mesh is pretty coarse here. As I told you in my video, this area is pretty much under high stress and deformation, so you need a very fine mesh in this area. So first thing you will have to do is to refine the mesh in this area where you have the contact between the indenter tip and the sample itself. So this needs to be refined. This should be okay, but this needs to be refined in this area for sure. And so I'm not going to look into the element type or something, because most probably this must be correct. And now if I go and run the analysis, it's going to take most probably a very long time. So I'm going to say explicit nano, and then I will just keep everything as I say. Always go with full precision and double precision for explicit, and then submit to see if everything is working fine or not. It might give some error because these elements are really big and they will start to distort as soon as the contact is established between the two surfaces. So let's go here and see what's happening. So there is a warning. This is all about whenever you apply displacement boundary condition, it asks you to check if amplitudes and everything are defined perfectly. Otherwise, it takes it as an instantaneous, and that will be like a jump. Okay, so I think it started running, and we should see something coming out soon. So you see it's going fine in my opinion, and yeah, so it's going good because element this is very coarse, so obviously it will be distorting now, and we can check that whenever by going to the results section and we press this. We have some value of stress. This means their contact is established, and you can already see there is a deformation going on, and obviously these elements will start to distort. Again, I have a nice video on adaptive meshing coming up, so you can use that as well in this case to refine the mesh, and also remeshing techniques. I have another video coming up on remeshing as well, so you can use that technique to also refine the mesh rather than going into the manual refinements if it works for your case. So you see it's going okay, but I mean these elements are not good enough, and you see you need to capture the whole deformation and indentation pattern, so you need a very fine mesh in this area. Okay, so I will go back and see what's happening in the job now. Monitor, so it has to go up to 1, so let it finish, and then I will show you what you can do. Right now it's a displacement control test. So this is how the actual test from the user looks like. The displacement goes up to 400 nanometers or slightly higher, and the loads for indentation depth, I think they should be, in my opinion, 4 because micronewtons, goes up to 7 millinewtons in my opinion, or 7,000 micronewtons if you know. So that's what they want to follow, and the user said that how can I apply this force rather than what we are applying right now, which is a displacement. In my opinion, if you don't know the material properties, then you can apply the displacement up to this point, and you can get this kind of curve and then see how far it is from the actual case, and then you start to fine-tune your elastic and plastic properties and see which parameters will give you the best fit, and that will be your material properties. But if you don't want to go to that road and you think their material properties are completely accurate, then what you can do is you run a displacement control test as you have done here. Go to the results, and now it should be up to 1. Okay, let me go back and go to results again. Now if I go, I need to close it. I think sometimes ABAQUS give us hard time. And now open again, or maybe go back, results. And now if I press, I should go up to total time of 1. And now if I rotate, so you see it's already distorting. If I remove this indenter thing here from here, which is this thing, and you see it looks something like this, and you're catching something, but still you can't get the actual profile, because you should get the tip profile which is indenting into the samples. But our aim is now to basically see how much is the force which is acting. The first thing is we just pushed it in, we never pulled it out. So first, if we know the displacement, let's say 400 nanometers or 2 millimeters or 1 millimeter or whatever, then in the load module, where we specify this amplitude, we need to give this amplitude as the test data. So in this case, at 0, let's say we applied a 0 displacement. At 0.9 we applied 1, and then we say at 1.0 it goes back to 0.0. okay, and in this case everything is elastic, so obviously we won't see that kind of hysteresis, because everything will follow. It will follow basically. If I bring that thing here, then you will see that it will not go like this, but it will go like this and comes back in the same path, because everything is elastic. But in plastic case it will change. So let's go with this and see what it looks like. So now if I go to visualization, and if I plot, let's say plot XY data, create field output, and then I say from unique nodal, I plot the reaction force in Z direction, because we applied the displacement in Z direction, and then we need to find the node which is relevant. So I think this reference point is the one which we are after. Let's see, it's not able to show us, but most probably this is the one. So let's plot this, and you see it goes there and it stays until this point. So the trend is very much the same what you see, but the forces are very high. These are in newtons, exponent 6. And now to get that effect of going down, so we need to, we already changed the amplitude function as I showed you here in the amplitude. So I have changed it from not going from 0 to 1 to 0 to 1, but rather it goes to 1 until 0.9, and then it unloads, so it goes back to 0 again. So let me run this quickly and I show you what it looks like then. As you can see, now analysis is almost finished. So let's go and look at the results, where we have a loading and unloading effect defined through amplitude function. So let's go to results, and this is how it looks like. So now if I go back, then you would see that it goes down until 0.9, and then it should come up, and that's what you see here. So this works fine. Now we go back to tools, XY data manager, create field output, again the same reaction force, and in this case I will also take the displacement u, which we are applying as a boundary condition from on the same node, and it's at the reference point, and I will save it for the time being. Now if I plot the reference node, then you can see, so if I plot this reference node now, reference force in 3 direction, then it looks something. So you see you have loading and then unloading, and that is the effect you see there. It's going like this because we are plotting as a function of time, but when we will be plotting as a function of displacement, you will see this will go like this, and then it will follow the same path because everything is elastic. So if I go create, operate on XY data, and then if I plot combine displacement and then reaction force on the vertical axis, save it as this, and then plot, then you see it's following almost the same path, right? And it's just because it's an elastic loading and unloading effect, because we don't have any plasticity defined until now. I'll delete this and I will keep that elastic one only as here. Now what I do, I go back and I change the properties, and I will change the properties of the material and make it elastic plastic. So this is one thing you have to do. So elastic properties are there, and for plasticity I'm going to use plastic option. Let's say if it's pure aluminium, which is very soft, so I define the material properties as 50 megapascals, and then plastic strain is 0. This is initial yielding, and then maybe I'm using a bilinear function, so let's say it goes up to 130 and then it goes up to a strain of 10. I'm just giving some fictitious value. You have to find the values which are more relevant to your case. And now if I go back and rerun it, so I should be able to see the result. So another thing you should note down here is we have stresses, but when we plot plastic strains, there are no plastic strains because they are not there, and we have some normal strains. So everything is elastic. That's what I wanted to say here. Now we go back to this, and then we should ensure that we have asked for the equivalent plastic strain, which is this one, so that we should be able to see that. For elastic analysis, it's 0, so it's not automatically giving us that. So now we go submit. And now, so two things we have changed from the initial model. One is the loading and unloading effect, and the second one is the elastic plastic property. So what we are after is actually we're trying to get this kind of trend, and then later on you can use fit the material parameters or change the loading to fit this with your experimental data. So I think it's running fine. So again, I will pause it and come back as soon as it's finished. As you can see now, the analysis is finished. So let's go and look at the results now. So again, to remind you, what we have changed here is we have included this to load and unload, and then also we have included the plasticity now in the model. So now if we go back and firstly look at the plastic strain, so we see we have plastic strain, and we see a lot of plastic strain due to the deformation here, and we can see element distortion, as you can see here as well. So it goes inside, and then it will come out after 4.9. See, that's how it looks like. And in the previous case, it was unloading, so it was coming back. But in this case, you have plastic deformation or permanent deformation. So you see this kind of response. Now you go to XY data, create, again, field outputs, unique nodal, and we're going to keep the same, and we will select the same node label as this one, and then save the data. Okay. So now we have saved the data. We go back to XY data manager, and these are our new values. And now we're going to create, if you plot this, now you will see slight differences because it's elastic plastic loading, and these oscillations are coming from the mesh because your mesh is starting to distort and trying to struggle basically. So these could be numerical errors as well. While this should be a straight line, as you can see, load and unload, because we are applying a displacement boundary condition. Okay, now what we do, we basically combine these, because I want to show you that hysteresis which will happen due to the plasticity. So now combine displacement and then reaction force, save S2, and then plot. And there it is. So it should go like this, and then it should come like this, and you can see this is what's happening here. Okay, so I hope this makes some sense. If I plot it with this, then you will see that one was going like this, and the elastic plastic is very low because your yielding starts at 50 megapascals, so it cannot take this much load. So now what I do, I bring this one back, and I show you how to apply force rather than the displacement, because that was the main question. So in this case, the force is going up to 20,000 or maybe 25,000. So I will apply a force of 20,000 until 0.9, and then I will upload again. I will unload again and see what we capture there. Again, you need to refine the mesh. I'm not showing you here. If you are interested, comment below, and I will show you. I will create a tutorial on how to refine the mesh around the indented area later on. Okay, so loading, displacements. This is the displacement. I'm going to get rid of it now. So instead of getting rid of it, I will just make it inactive. So now it's gone. So I'm not deleting it rather than just inactive, making it inactive, because I can bring it back later on if I want it. Now I go to the loads, create concentrated force I need, and I will apply on this reference point, CF3, and you remember it was around 20,000. So let's apply 20,000 or something, or let's apply 2,000. I don't know it will create anything or not. And then for the load amplitude function, I'm using the same. So this force will be applied such that it will start from 0, go to 2000 until 0.9 seconds, and then it will go back to 0, and that is the unloading step. Okay. So this is your force now, and now let's run it. In explicit, it's very easy because when you apply a force, you have a rigid body motion, and explicit already has the inertia terms, etc. So it shouldn't be any problem. But when you are in standard analysis, You might come up with singularities, and again I have a video on how to remove those singularities, so please have a look at my channel on how to remove these numerical singularities coming from rigid body motion in standard analysis. But overall process which I am showing you here is the same for standard as well. Now I go and submit. And I will pause the video and I will come back once it's finished. Now as you can see, the simulation is finished, and we're gonna go and now look at the results. With in this case, we remember it was a force control test rather than a displacement control test. So if I press this, if I go back, then you see it goes down and then it just relaxes as the force is being removed. But it doesn't move significantly because in the previous case we had a displacement, so displacement was fixed. So now let's go and see what is happening here. And again, so if you are whatever data you are getting from experiments, whether displacement control or force control, you can apply through the amplitude function as I showed you today in this video. So this could be valid for any other test as well. Now let's go and see what it looks like as in terms of the plotting of the results. So I'm going to delete the previous one, which was elastic plastic case, because we already have XY data too. Now I'm going to go and first get the field data from field output, node sets, reference point, save. And next I'm going to combine them together. So operate on data, combine option, displacement, and then this force, and then save. So this is there. So now if I plot this, so you see it's all zero. So yeah, because we took the reaction forces, but in this case we are applying a force, so we need to plot the forces rather than the reaction forces. So I go back and I will select the forces, and I think I haven't asked for the force output here. So if I go back to the step module, and if I find out the forces and reaction forces, then here I can ask for the concentrated forces and moment. So once you have this, then you will be able to plot that as I have shown you today in the other case. Instead of CF3, the RF3, you will definitely get CF3, and then you can plot that directly as I did it for RF3. And then if you will see it, then it will be very much similar to what you see, that is the loading and then some unloading part coming in. And obviously unloading will not go up to this point, but unloading will go somewhere until it relaxes, because you're not applying a displacement boundary condition. So let me try to run it, because I have 5-10 minutes before I have to go somewhere. So I will pause this and then come back as soon as it's finished. Okay, so as you see, this is now finished. So let's go and now try our luck one more time. So this also is a learning lesson, that always make sure before running your job that what parameters you need, everything is defined correctly. If your job is taking a long time and you run it and then you find out, oh, you missed something, then you have to restart everything again. So be careful. We are doing it in a quick time here, so you can see even I am making a lot of mistakes. So now again, create field output, unique nodal, and in this case I have to go with concentrated forces, so I'm going to select CF3. Hopefully it's going to work, and generally it doesn't. And then save. Now let's see if this concentrated force is really stored or not. So you see it goes up and then goes down. Most probably it's elastic, that's why you are seeing a linear response here. So I will delete this because this is 0. There is no reaction force since we haven't applied a displacement boundary condition. Now I'm going to combine these two together. So I will say operate on XY data and then combine displacement and then force, save data 4. And now if I plot XY data 4, so you see it goes up there. So there is some plasticity and then it comes back again. This mesh is really, I don't like it because it is showing a certain amount of deformation, which is causing this force too high. So again, so this way, if you compare these two, then you can see how it looks like. So this one was this one was the one which reaction forces. I will delete this. So this one was with elastic plastic response. This one is also elastic plastic, but now it's a force control test, and force is very low. So you should see a very small force and displacement curve here as compared to the displacement which you're applying, because you only applied a force of 2000 newtons or something, which is going there. So this way you can just fine tune your parameters, optimize your mesh, fine tune your material parameters, and then should be able to fit the experimental curve as what you want to really get from your test. And this will be your, that will be your material properties and the correct simulation of your nano indentation test. I hope I was able to answer all the questions which were asked by the subscriber. If I have missed anything, then please feel free to comment below, or if you have any further question, then also please feel free to contact me directly or comment below or comment on any of my video. So I'll come back with some more interesting videos in near future. So till then, enjoy your time and have a great day in the week. Bye.